Subscribe to the channel so you don't miss out on any of these videos. Imagine a time when the universe was young, so young that galaxies as we know them hadn't even formed yet. Darkness stretched endlessly across the void, broken only by tiny flickers of light. These lights weren't just any stars, they were monsters. Stars so massive, so powerful, that they make the sun look like a speck of dust in comparison. These were the supermassive stars of the early universe, the very first generation of stars to ever exist. They lived fast, burned brightly, and died in cataclysmic explosions that shaped everything we see in the cosmos today. But here's the thing, these stars were so colossal and so strange that scientists are still trying to figure them out. How did they form? Why were they so much bigger than the stars we see now? And how did their violent deaths create the building blocks for galaxies, planets, and even life itself? The answers to these questions are like pieces of a cosmic puzzle, scattered across space and time, waiting to be uncovered. These stars weren't just massive, they were fundamental. They kick-started the process of cosmic evolution, taking a universe filled with almost nothing but hydrogen and helium and transforming it into the rich, complex place we live in today. Yet, despite their significance, we've never seen one. They existed long before Earth, long before the Milky Way, and their remnants have been scattered and hidden by billions of years of cosmic history. But their fingerprints are everywhere, in the chemical makeup of stars, in the distribution of galaxies, and even in the elements that make up your body. Yes, you heard that right. The iron in your blood and the calcium in your bones? They were forged in the fiery deaths of these supermassive stars. Let's take a step back to understand why these stars were so different from the ones we see today. The first thing to know is that the early universe was a very simple place. After the Big Bang, the cosmos was filled with a hot, dense soup of particles that eventually cooled down enough to form atoms. For hundreds of millions of years, the universe was a dark and boring expanse of hydrogen and helium gas. There were no heavy elements like carbon, oxygen, or iron. Those didn't exist yet. Without these elements, the process of star formation was fundamentally different. The gas clouds that collapsed to form the first stars didn't have the same cooling mechanisms that modern star-forming regions have. This meant that these early stars grew to be enormous, up to hundreds, or even thousands of times the mass of the Sun. Think about that for a second. The largest stars we see today might reach 100 to 150 times the Sun's mass. But these early monsters dwarfed even that. They burned at millions of degrees, shining with an intensity that's hard to comprehend. And they were short-lived, so short-lived that their entire life cycle might have lasted just a few million years, a blink of an eye on cosmic timescales. When they ran out of fuel, they didn't just fizzle out quietly. They exploded in titanic supernovae or even more dramatic events called parainstability supernovae, releasing unimaginable amounts of energy and scattering their material across the universe. But why does this matter? Because these explosions were the first steps in creating the universe we know today. When these stars died, they seeded the cosmos with heavy elements, carbon, oxygen, nitrogen, iron, all the things needed to form planets, oceans, and living organisms. Without these supermassive stars, the universe might still be a barren expanse of hydrogen and helium. They were, quite literally, the first creators. And here's where things get even more fascinating. These stars might have been responsible for triggering the formation of the first black holes, the seeds of the supermassive black holes we see at the centers of galaxies today. Imagine a star so massive that when it collapses, it doesn't just form a black hole, it forms a black hole millions of times the mass of the Sun. These black holes would have grown over time, swallowing up gas and merging with other black holes to become the monstrous objects we see today, shaping the structure of galaxies in the process. But how do we know any of this? After all, these stars existed over 13 billion years ago, far beyond the reach of even the most powerful telescopes. The truth is, much of what we know comes from indirect evidence. Scientists study the chemical composition of ancient stars, looking for clues about the first generation of stars that came before them. They run complex simulations, recreating the conditions of the early universe to see how these stars might have formed and evolved. And they search for the faintest signals of light, hoping to catch a glimpse of the earliest moments of cosmic history. One of the biggest mysteries surrounding these stars is how they formed in the first place. The early universe wasn't exactly a friendly place for star formation. The gas clouds were hot, and without heavier elements to help cool them down, it's not entirely clear how these clouds managed to collapse into stars. Some scientists think that dark matter, an invisible substance that makes up most of the universe's mass, might have played a role. Dark matter could have acted as a kind of gravitational glue, helping to pull the gas together and kickstart the process of star formation. Another mystery is what happened to these stars after they died. Did they all collapse into black holes? Or did some of them leave behind other kinds of remnants, like neutron stars or exotic forms of matter that we haven't discovered yet? And if they did form black holes, how did those black holes grow and evolve over time? These questions are at the forefront of modern astrophysics, and answering them could unlock some of the deepest secrets of the universe. There's also the question of scale. If these stars were so massive, why don't we see stars like them today? Part of the answer lies in the changing conditions of the universe. As the first generation of stars created heavier elements, the nature of star formation changed. Modern stars form in environments rich in metals, which act as cooling agents and limit the size of the stars. But it's also possible that we simply haven't found the most massive stars in the modern universe. After all, the cosmos is a big place, and there's still so much we don't know. And then there's the tantalizing possibility that some of these first-generation stars, or at least their remnants, might still exist. While most of them would have burned out long ago, it's possible that a few of their black hole remnants have survived to this day, lurking in the depths of space. Finding one of these relics would be like finding a time capsule from the dawn of the universe, offering a direct window into an era we can only imagine. The story of these supermassive stars is far from over. Every new discovery, every new piece of data, brings us closer to understanding these cosmic titans and their role in shaping the universe. And as our telescopes grow more powerful and our simulations become more accurate, we're bound to uncover even more about these mysterious giants. Understanding the role of supermassive stars in cosmic evolution takes us deeper into some of the most profound questions about our universe. One of the key aspects to consider is how these stars might have affected their surroundings. Supermassive stars didn't just sit quietly in the void. Their incredible energy output fundamentally transformed the regions around them, triggering a process called reionization. Reionization is one of the most important events in cosmic history. It's the moment when the universe became transparent, allowing light to travel freely for the first time. Here's how it works. In the early universe, before the first stars ignited, most of the gas was neutral hydrogen. This means that the atoms were whole, with their electrons tightly bound to their nuclei. Neutral hydrogen is good at absorbing light, so the universe was effectively opaque. But when the first stars formed, their intense radiation began breaking apart these hydrogen atoms, knocking off their electrons and turning them into ionized hydrogen. This process of ionization spread outwards, creating bubbles of transparency around each star. Over time, as more and more stars were born, these bubbles grew and overlapped, eventually making the entire universe transparent. The first supermassive stars were likely the main drivers of this reionization process. Their extreme ultraviolet radiation would have been incredibly effective at ionizing hydrogen, clearing the way for light to travel freely. Without these stars, the universe might have remained dark and opaque for much longer, delaying the formation of galaxies and the complex structures we see today. But reionization wasn't just about making the universe transparent. It also changed the way matter clumped together to form larger structures. Before reionization, gas could cool and collapse relatively easily, forming stars and galaxies. But as the gas became ionized, it also became hotter and less likely to collapse under gravity. This created a feedback loop, where the formation of stars made it harder for new stars to form. Supermassive stars, with their immense energy output, played a key role in this feedback process, shaping the structure of the universe on the largest scales. Another fascinating aspect of these early stars is their connection to the mysterious dark matter that pervades the universe. While dark matter doesn't interact with light or normal matter in the same way we're used to, it does exert a gravitational pull. This pull might have been crucial in helping the first gas clouds collapse to form stars. Some theories even suggest that the first supermassive stars could have formed in the dense cores of dark matter halos, regions where dark matter was especially concentrated. If this is true, then studying these stars could provide valuable insights into the nature of dark matter itself, one of the biggest unsolved mysteries in science. And speaking of unsolved mysteries, let's not forget the role of supermassive stars in the formation of black holes. Black holes are some of the strangest and most fascinating objects in the universe, and their origins are still a topic of intense debate. The first supermassive stars may have been the seeds of what would later become supermassive black holes, the gargantuan objects found at the centers of most galaxies, including our own Milky Way. These early black holes could have grown rapidly, merging with other black holes and swallowing up nearby gas to become the colossal monsters we see today. But here's the kicker: some of these black holes grew so quickly that we can't fully explain how it happened. Observations have found supermassive black holes that existed when the universe was less than 1 billion years old. That's astonishingly early, considering how long it takes for black holes to grow. One possibility is that these black holes started out with a huge advantage, forming from the collapse of the first supermassive stars, which would have given them a significant head start. This idea is supported by simulations, which show that massive black holes could indeed form from the remnants of these stars under the right conditions. These early black holes didn't just sit quietly in the background. As they grew, they would have released enormous amounts of energy, creating what are known as quasars, some of the brightest and most energetic objects in the universe. Quasars are powered by gas and dust falling into black holes, a process that releases incredible amounts of radiation. The light from these quasars traveled across the cosmos, providing a glimpse into the early universe. In fact, some of the most distant quasars we've observed may be connected to the remnants of these first supermassive stars. So, why don't we see supermassive stars forming today? The answer lies in the changing conditions of the universe. In the early universe, the lack of heavy elements made it possible for stars to grow to enormous sizes. But as these stars died and seeded the cosmos with heavy elements, the environment for star formation changed. Heavy elements allow gas clouds to cool more efficiently, which means that modern stars tend to form in smaller, more stable sizes. The unique conditions that allowed supermassive stars to form simply don't exist anymore. Still, the legacy of these stars is all around us. Every time we look up at the night sky, we're seeing galaxies, stars, and planets that owe their existence to the explosive deaths of the first supermassive stars. The very atoms in your body, the carbon, oxygen, and nitrogen that make life possible, were forged in the fiery cores of these ancient giants. In a way, we're all connected to these stars, living proof of their profound impact on the universe. But there's still so much we don't know. For example, could there be other mechanisms, beyond what we currently understand, that allowed these stars to form? Could some of their remnants still be lurking in the universe, waiting to be discovered? And what can these stars tell us about the ultimate fate of the universe? Scientists are constantly pushing the boundaries of knowledge, using advanced telescopes and simulations to uncover the secrets of these cosmic titans. One of the most exciting developments in this field is the advent of next-generation telescopes like the James Webb Space Telescope. With its ability to peer deeper into the universe than ever before, the James Webb could provide direct evidence of the first generation of stars. It might even detect the faint afterglow of their explosive deaths, offering a new window into this mysterious era of cosmic history. The James Webb Space Telescope, often described as a time machine, has been designed specifically to explore the universe's earliest moments. Its unparalleled infrared capabilities allow it to cut through cosmic dust and detect faint light emitted billions of years ago. This makes it the perfect tool to study the remnants, or traces of the first supermassive stars. While we haven't yet observed these ancient giants directly, the Webb telescope could uncover indirect evidence by finding the chemical fingerprints left behind by their explosive deaths. This includes the unique ratios of elements like carbon, nitrogen, and oxygen that were produced during their lifespans. The discovery of these chemical signatures in distant galaxies could confirm the existence of supermassive stars and reveal their role in shaping the universe. Moreover, the Webb telescope might even capture evidence of population 3 stars, an elusive category that includes the very first stars to form after the Big Bang. While not all population 3 stars were supermassive, many of them likely reached sizes far beyond anything we see today. Observing these stars would give us an unprecedented glimpse into the universe's earliest days, helping us piece together the story of how it evolved from a primordial soup of hydrogen and helium into the complex cosmic web we see today. But here's something even more intriguing. If the first supermassive stars formed in regions of intense dark matter concentration, their deaths might have left behind clues about the nature of dark matter itself. Some theories suggest that dark matter particles could interact in ways that influence the formation and behavior of stars. For instance, certain types of dark matter could theoretically produce heat through self-annihilation, a process that might have impacted the size and lifespan of early stars. If these interactions occurred, they might have left detectable imprints in the remnants of these stars, or the galaxies they helped shape. This connection between supermassive stars and dark matter is one of the most exciting frontiers in astrophysics. By studying the earliest stars, scientists could uncover not only the origins of visible matter but also the hidden scaffolding of dark matter that underpins the universe. This could lead to groundbreaking discoveries about the fundamental forces that govern cosmic evolution. Another fascinating aspect of supermassive stars is their potential role in triggering the formation of galaxies. In the early universe, these stars were likely surrounded by immense clouds of gas and dust. When they exploded as hypernovae, the energy released would have sent shockwaves rippling through these clouds, compressing the gas and kickstarting the formation of new stars. This process, known as positive feedback, might have been crucial in jump-starting the rapid growth of early galaxies. Moreover, the immense radiation emitted by supermassive stars could have driven powerful stellar winds, blowing gas and dust outward and shaping the structure of their host galaxies. These winds might have also influenced the distribution of heavy elements, spreading them across vast distances and enriching the intergalactic medium. This widespread enrichment was essential for the formation of later generations of stars, as heavy elements play a key role in cooling gas clouds and enabling star formation. But not all the effects of these stars were constructive. Their intense radiation and powerful winds could also have had a destructive side, stripping away gas from nearby regions and suppressing the formation of new stars. This dual role, both creating and destroying, underscores the complex interplay between supermassive stars and their environments. Understanding this interplay is key to unraveling the story of how galaxies evolved over billions of years. One of the enduring mysteries about these stars is the question of their final moments. We know that supermassive stars likely ended their lives in cataclysmic explosions, but the exact details of these events remain uncertain. Traditional supernovae, the explosive deaths of regular stars, may not be sufficient to describe what happened when a supermassive star collapsed. Instead, these stars might have undergone a process known as parent stability supernova, a rare type of explosion that occurs when the star's core becomes so hot that gamma rays create particle-antiparticle pairs. This process destabilizes the star, leading to a complete and total explosion with no remnant left behind, not even a black hole. Alternatively, if the star was massive enough, it might have collapsed directly into a black hole without an intermediate supernova phase. In this scenario, the collapse would have released an enormous burst of energy in the form of gamma rays, creating a gamma ray burst, GRB. GRBs are some of the most energetic events in the universe, and their origins are still a subject of intense study. If even a fraction of GRBs are linked to the deaths of supermassive stars, they could provide a new way to study these ancient titans. But what if some of these stars didn't collapse at all? Some theoretical models propose the existence of exotic objects known as quasi-stars, which are essentially massive clouds of gas surrounding a nascent black hole. These objects could emit enormous amounts of radiation for millions of years before eventually collapsing entirely. If quasi-stars existed, they might represent an intermediate stage between supermassive stars and the formation of the first supermassive black holes. While much of this remains speculative, new observations and simulations are helping scientists narrow down the possibilities. For example, researchers are using computer models to simulate the behavior of massive stars in the early universe, testing different scenarios to see which ones best match the observed properties of galaxies and black holes. These simulations have already revealed surprising insights, such as the possibility that supermassive stars could form through the merger of smaller stars in dense star clusters. If this is true, it could explain how these stars grew so large in such a short amount of time. But perhaps the most exciting possibility is that we might one day find direct evidence of a surviving remnant from one of these stars. While most supermassive stars likely ended their lives billions of years ago, it's possible that some of their black hole remnants are still out there, hidden in the depths of space. Detecting these remnants would be like finding a fossil from the dawn of the universe, a tangible link to the very first chapter of cosmic history. As we continue to explore the universe, the mysteries of supermassive stars remind us of just how much we still have to learn. These ancient giants were the architects of the early cosmos, shaping the universe in ways we are only beginning to understand. Their story is a testament to the power of curiosity and the human drive to uncover the unknown. The idea that some remnants of supermassive stars might still exist today is not as far-fetched as it seems. Black holes formed from their colossal collapses could be scattered across the universe, silently lurking in the void. Unlike supermassive black holes found at the centers of galaxies, these smaller black holes, known as intermediate mass black holes, might represent a missing link in our understanding of cosmic evolution. They could bridge the gap between the relatively small black holes formed from modern stars and the gargantuan black holes millions or even billions of times the mass of the Sun. The challenge is finding them. Intermediate mass black holes are elusive by nature. Without a consistent source of nearby matter to consume and emit detectable X-rays, they remain almost invisible. However, advancements in gravitational wave astronomy are beginning to offer new ways to detect these hidden objects. When black holes collide, they send ripples through space-time that we can now measure on Earth. By analyzing these signals, scientists might one day identify collisions involving intermediate mass black holes, providing direct evidence of their existence. If intermediate mass black holes formed from the deaths of the first supermassive stars, their discovery could offer profound insights into the conditions of the early universe. For instance, the distribution of these black holes might reflect the distribution of matter in the primordial cosmos, offering clues about the role of dark matter and the large-scale structure of the universe. Moreover, studying their properties could help us understand the mechanisms that allowed supermassive black holes to grow so quickly in the first billion years after the Big Bang. Speaking of rapid growth, one of the most puzzling questions about the early universe is how supermassive black holes managed to accumulate so much mass so quickly. The first quasars, galaxies with supermassive black holes at their centers emitting immense amounts of energy, have been observed less than a billion years after the Big Bang. Given the relatively short amount of time available, it's unclear how these black holes could have grown to billions of solar masses so early in cosmic history. One possible explanation is that supermassive stars played a crucial role. Their direct collapse into massive black holes could have provided a head start, creating seed black holes that were already thousands of times the mass of the Sun. These seeds would have had a significant advantage in accreting additional matter, allowing them to grow rapidly into the supermassive black holes we observe today. This scenario is particularly compelling because it connects the life cycle of the first stars to the formation of some of the universe's most enigmatic objects. Another possibility is that the conditions of the early universe allowed for faster black hole growth. During the first few 100 million years after the Big Bang, the universe was much denser and richer in gas than it is today. This abundance of material could have provided an ample supply of fuel for black holes to grow at unprecedented rates. Additionally, the lack of heavy elements in the early universe meant that gas clouds were less prone to fragmentation, potentially leading to the formation of massive, direct collapse black holes without the need for an intermediate stellar phase. This brings us back to the unique environment of the early universe and how it enabled the existence of supermassive stars in the first place. Unlike today's universe, where stars form in relatively cool and stable molecular clouds, the first stars formed in a much hotter and more chaotic environment. The lack of heavy elements meant that gas clouds were less efficient at cooling, requiring much larger amounts of gas to collapse under their own gravity. This is why the first stars, including supermassive stars, were so much larger than anything we see today. But there's another factor to consider: the role of cosmic radiation. In the aftermath of the Big Bang, the universe was filled with intense radiation that could have influenced the formation of the first stars. For example, high-energy photons could have ionized gas, creating conditions that favored the formation of extremely massive stars. At the same time, this radiation could have inhibited the formation of smaller stars, further tilting the balance toward the creation of supermassive objects. The interplay between radiation, gravity, and gas dynamics is an area of active research, with scientists using sophisticated simulations to recreate the conditions of the early universe. These simulations have revealed that the formation of supermassive stars was likely a rare and highly localized phenomenon, occurring only in regions with the right combination of factors. This rarity makes the study of these stars even more important, as they represent a unique and fleeting chapter in the history of the cosmos. One of the most surprising findings from these simulations is the possibility that supermassive stars might have formed in pairs or even larger groups. In dense regions of gas, gravitational interactions could have caused multiple stars to form close together, influencing each other's growth and evolution. If this happened, the interactions between these stars could have produced spectacular phenomena, such as collisions or mergers that released enormous amounts of energy. These events might have left behind observable traces, such as bursts of radiation or gravitational waves, that we could still detect today. The idea of supermassive stars forming in groups also raises intriguing questions about their role in the chemical evolution of the universe. If these stars exploded as hypernovae, their combined output of heavy elements would have enriched their surroundings far more quickly than individual stars could. This rapid enrichment might have accelerated the transition from the first generation of stars to later generations, setting the stage for the formation of galaxies like our own Milky Way. But the legacy of supermassive stars extends beyond their physical remnants. Their brief and brilliant lives likely had profound effects on the cosmic environment, influencing everything from the distribution of matter to the formation of new structures. For instance, the intense radiation emitted by these stars could have ionized large regions of the universe, contributing to a process known as reionization. This was a pivotal era in cosmic history when the first light began to shine through the darkness, transforming the universe from an opaque fog to the transparent expanse we see today. Reionization is one of the most mysterious periods in the history of the universe, and supermassive stars might have been key players in this transformation. By emitting vast amounts of ultraviolet light, these stars could have provided the energy needed to ionize hydrogen atoms, breaking them apart into protons and electrons. This process would have created bubbles of ionized gas that eventually grew and merged, clearing the way for light to travel freely through the cosmos. The connection between supermassive stars and reionization highlights their importance not just as individual objects but as drivers of cosmic evolution. These stars were not isolated phenomena. They were deeply interconnected with the broader processes that shaped the universe. Their lives and deaths helped to forge the conditions for the emergence of galaxies, stars, and planets, ultimately laying the groundwork for the existence of life itself. The role of supermassive stars and reionization also sheds light on how they might have influenced the early development of galaxies. These stars, with their intense radiation and powerful winds, could have shaped their surroundings in dramatic ways. For instance, the radiation from a single supermassive star would have created immense bubbles of ionized gas, pushing away nearby material and altering the density of the surrounding region. This feedback mechanism, often referred to as radiative feedback, could have prevented the formation of smaller, less massive stars in the immediate vicinity, focusing the available gas into larger structures. At the same time, the intense gravitational pull of the massive stars themselves may have encouraged gas to collapse into dense regions, seeding the formation of new stars and star clusters. This delicate balance between radiation pressure and gravitational collapse would have played a crucial role in determining the size and structure of the first galaxies. The interplay between these forces is an area of active research, as it helps us understand not only how galaxies began to form but also why we see such a diversity of galaxy types today. Beyond their immediate surroundings, supermassive stars might have also influenced the larger-scale structure of the universe. By releasing energy and matter into the cosmos, these stars contributed to the turbulent motions of gas and the formation of large-scale filaments that make up the cosmic web. This vast network of interconnected structures spans the universe, with galaxies and galaxy clusters forming at the intersections of these filaments. The energy and heavy elements produced by the first generation of stars likely played a significant role in shaping this intricate framework. But despite their outsized influence, direct observational evidence of supermassive stars remains elusive. Since these stars lived and died billions of years ago, their light has long since faded. However, astronomers are beginning to uncover indirect evidence of their existence through a variety of innovative techniques. For example, by studying the chemical composition of ancient stars in our galaxy, scientists can infer the types of processes that occurred during the earliest epochs of star formation. Certain elements, such as carbon, oxygen, and magnesium, appear in ratios that are consistent with the nucleosynthesis processes expected from supermassive stars. Similarly, the detection of extremely distant galaxies with unusual properties provides additional clues. Some of these galaxies exhibit signs of intense ionization, suggesting the presence of massive stars or black holes that could have been remnants of the first supermassive stars. Observations of these galaxies using advanced telescopes, such as the James Webb Space Telescope, JWST, are beginning to shed light on the physical conditions of the early universe and the role of massive stars in shaping it. The JWST, in particular, has opened new doors in the quest to understand supermassive stars. With its unprecedented sensitivity to infrared light, the telescope can peer farther into the cosmos than ever before, capturing light emitted during the earliest stages of the universe. Astronomers are using the JWST to search for the telltale signatures of population 3 stars, the first generation of stars, which includes supermassive stars. By analyzing the spectra of distant galaxies, they hope to identify the unique chemical fingerprints left behind by these ancient giants. One of the most exciting possibilities is that the JWST might detect direct evidence of supermassive stars in the form of gravitational lensing. This phenomenon occurs when the gravity of a massive object, such as a galaxy cluster, bends the light from a more distant source, magnifying it like a cosmic telescope. If supermassive stars were bright enough, their light could have been magnified by gravitational lensing, allowing us to observe them even billions of years after they ceased to exist. While no such detections have been confirmed yet, the prospect of glimpsing these elusive objects is tantalizing. Another avenue of research involves studying the remnants of supermassive stars in the form of ancient black holes. As mentioned earlier, intermediate mass black holes are one possible outcome of the collapse of these stars. By searching for these black holes in the centers of globular clusters or in isolated regions of space, astronomers hope to piece together the history of the first stars. The discovery of even one confirmed intermediate mass black hole could revolutionize our understanding of how the first black holes formed and grew in the early universe. Gravitational wave astronomy also offers a promising path forward. The detection of mergers involving intermediate mass black holes could provide direct evidence of their existence and origins. Advanced detectors like LIGO and Virgo have already observed collisions between smaller black holes, and future upgrades could make it possible to detect signals from more massive objects. If intermediate mass black holes formed from the collapse of supermassive stars, their mergers would produce distinctive gravitational wave patterns that could reveal their ancient history. The search for supermassive stars and their remnants is not just a quest to understand the past. It also has profound implications for the future of astrophysics and cosmology. By studying these objects, we can test fundamental theories about the nature of gravity, the behavior of matter at extreme densities, and the evolution of the universe itself. Supermassive stars are more than just relics of a bygone era. They are key to unlocking some of the deepest mysteries of existence. For instance, the study of supermassive stars could help answer one of the most profound questions in cosmology: How did the universe transition from its early chaotic state to the structured, dynamic cosmos we see today? The immense energy released by these stars likely played a pivotal role in this transformation, driving the processes that led to the formation of galaxies, stars, and planets. By unraveling the story of these ancient giants, we can gain a deeper appreciation for the forces that shaped the universe and our place within it. The legacy of supermassive stars is written across the cosmos, from the chemical composition of ancient stars to the sprawling structure of the cosmic web. Their brief lives were a symphony of creation and destruction, leaving behind a universe forever changed. As we continue to push the boundaries of observation and theory, we move closer to uncovering the full story of these extraordinary objects and their role in the grand narrative of the cosmos. The lingering questions about supermassive stars extend to their formation. How could stars reach such incredible masses in the harsh environment of the early universe? While current models provide intriguing possibilities, there's still no definitive answer. One hypothesis suggests that these stars formed directly from massive clouds of primordial gas. Without heavier elements to cool the gas and encourage fragmentation into smaller stars, the clouds might have collapsed directly into enormous singular stars, reaching hundreds or even thousands of times the mass of our Sun. This idea ties into what astrophysicists call monolithic collapse. In this scenario, vast amounts of hydrogen and helium, left over from the Big Bang, rapidly coalesce under their own gravity. The result is a supermassive star that burns brightly and briefly before collapsing into a black hole or dispersing its material into space. However, such a process would have required very specific conditions: low turbulence, minimal rotation, and an isolated environment free from nearby competing gravitational forces. The rarity of these conditions might explain why supermassive stars were exclusive to the early universe. Another theory involves accretion. In this model, a smaller seed star forms first. Perhaps 50 to 100 times the mass of the Sun's surrounding gas is then drawn toward the seed star, feeding its growth and allowing it to reach supermassive proportions. This process could have been aided by the absence of heavy elements, which would normally provide resistance to gas flow and slow down accretion. Accretion is a compelling explanation, but it raises further questions. How did such large amounts of gas remain bound to the forming star, rather than being expelled by the immense radiation pressure generated by the star's intense heat? A third possibility involves collisions between stars. In the crowded, dense environments of the early universe, stars might have formed in clusters where interactions were frequent. In such a chaotic setting, collisions and mergers between massive stars could have created supermassive stars. This theory is supported by simulations showing that dense star-forming regions can lead to runaway collisions, with the most massive star in a cluster acting like a gravitational magnet, pulling in and merging with others. Regardless of the formation mechanism, the brief lifetimes of supermassive stars meant they lived fast and died young. These stars likely only existed for a few million years, a blink in cosmic time. Their rapid evolution and explosive deaths as supernovae or direct collapse events would have injected vast amounts of energy and elements into their surroundings. But exactly how these processes unfolded is still a mystery. One of the most puzzling aspects of supermassive stars is their internal structure and stability. The extreme mass of these stars would have created immense pressures at their cores, driving nuclear fusion at unprecedented rates. However, this same pressure would have also pushed the limits of hydrostatic equilibrium, the delicate balance between the outward pressure of radiation and the inward pull of gravity. Could supermassive stars have maintained this balance, or were they always teetering on the edge of collapse? Modern computational simulations offer some insights. They suggest that supermassive stars might have had convective interiors, with hot plasma rising from the core and cooler materials sinking back toward it. This convective motion could have distributed energy more evenly throughout the star, helping to prevent instability. But such models remain speculative, as the physical conditions within these stars are so extreme that they defy easy modeling. Another complication is the role of rotation. If supermassive stars spun rapidly, their centrifugal forces could have counteracted some of the effects of gravity, altering their structure and evolution. Rapid rotation might also have caused the stars to eject material, forming surrounding disks or jets of gas and radiation. Such features could have influenced the early formation of galaxies and contributed to the distribution of matter in the universe. As we consider the final stages of supermassive stars, the question of their collapse looms large. Unlike smaller stars, which often end their lives in supernova explosions that leave behind neutron stars or white dwarfs, supermassive stars might have skipped this intermediate stage entirely. If their cores became dense enough, they could have collapsed directly into black holes, without an explosive outburst. This process, known as direct collapse, is a leading theory for the formation of the first black holes, which later grew into the supermassive black holes we observe at the centers of galaxies today. Direct collapse would have produced enormous amounts of gravitational energy, possibly emitting powerful bursts of radiation in the form of gamma rays. These bursts might have been detectable even across the vast distances of the universe, though finding evidence of such ancient events remains a challenge. Some researchers speculate that gamma ray bursts observed today could be echoes of these primordial phenomena, offering a tantalizing link to the universe's earliest epochs. If supermassive stars did collapse into black holes, they could have provided the seeds for the growth of supermassive black holes that are billions of solar masses today. But how could these black holes grow so quickly in the relatively short time available between the birth of the universe and their observed presence in the early cosmic epochs? This black hole growth problem is one of the most significant puzzles in modern astrophysics. One possibility is that the remnants of supermassive stars were already massive enough to jumpstart the process. A black hole formed from the collapse of a supermassive star could have had a mass of thousands of suns, far larger than the black holes typically formed by smaller stars. These intermediate mass black holes would have had a significant head start in their growth, quickly accreting matter from their surroundings and merging with other black holes to reach supermassive scales. The role of supermassive stars in creating the universe as we know it cannot be overstated. Their formation, evolution, and eventual demise set the stage for the emergence of galaxies, the distribution of elements, and the growth of black holes. As astronomers continue to refine their models and improve their observational techniques, we move closer to unraveling the secrets of these cosmic behemoths. Despite the progress, many questions remain unanswered. Did supermassive stars exist in isolation, or were they part of larger structures like protogalaxies? What conditions favored their formation, and why don't we see similar stars forming today? Could the remnants of these stars still be influencing the universe in subtle, undetected ways? These mysteries ensure that the study of supermassive stars will remain a vibrant and exciting field for years to come. The story of supermassive stars is one of extremes, extreme sizes, extreme temperatures, and extreme consequences for the cosmos. They were the universe's first great experiments in star formation, pushing the boundaries of what is possible and leaving an indelible mark on the fabric of space and time. As we continue to explore the heavens, the echoes of these ancient giants remind us of the incredible forces that shaped our universe, and the enduring mystery of the stars that lit up the cosmic dawn. The cosmic legacy of supermassive stars doesn't just lie in their dramatic life cycles, it extends to the profound influence they had on the universe's structure, composition, and evolution. When these massive stars ended their lives, whether as explosive supernovae or through direct collapse into black holes, they profoundly altered their surroundings. They were instrumental in enriching the primordial universe with heavy elements, influencing the formation of galaxies, and driving the cosmic phenomena we observe today. One of the most significant contributions of supermassive stars was their role in cosmic nucleosynthesis. In their cores, these stars fused hydrogen and helium into heavier elements like carbon, oxygen, and even elements as heavy as iron. These processes created the first generation of heavy elements, referred to as metals, in astrophysical terms, which were absent in the primordial universe. When these stars exploded or shed their outer layers, they dispersed these elements into the surrounding interstellar medium, creating the chemical building blocks for the next generations of stars, planets, and eventually, life itself. This process of metal enrichment fundamentally changed the dynamics of star formation in the universe. The presence of heavier elements allowed subsequent stars to form more efficiently by enabling gas clouds to cool more rapidly. This cooling effect caused the clouds to fragment into smaller clumps, resulting in the formation of less massive stars, similar to the ones we see today. In this sense, supermassive stars were transitional objects, bridging the gap between the primitive, metal-poor conditions of the early universe and the more complex and diverse environments we observe in the present day. Beyond chemical enrichment, the intense radiation emitted by supermassive stars also played a critical role in shaping the early universe. These stars emitted copious amounts of ultraviolet light, capable of ionizing neutral hydrogen gas. This process, known as cosmic reionization, was a pivotal event in the universe's history. By reionizing the gas, supermassive stars helped to lift the fog of the cosmic dark ages, making the universe transparent to light and paving the way for the large-scale structures we observe today. Cosmic reionization is thought to have occurred in patches, as the ultraviolet radiation from clusters of supermassive stars carved out bubbles of ionized gas. Over time, these bubbles expanded and merged, eventually reionizing the entire universe. However, the exact contribution of supermassive stars to this process remains a topic of active research. Could they have been the primary drivers of reionization, or were other sources, such as early galaxies or black hole accretion disks, also significant contributors? Observations of distant galaxies and the cosmic microwave background are helping to shed light on this question, but definitive answers are still elusive. The gravitational influence of supermassive stars also left an indelible mark on the universe. As these stars collapsed into black holes, they may have acted as the gravitational anchors around which early galaxies formed. The interplay between the forming black holes and their surrounding matter could have driven the rapid growth of galaxies, shaping their structures and influencing their evolution. In this way, the remnants of supermassive stars may have seeded the universe's most massive and energetic objects, quasars and supermassive black holes. Quasars, the extremely luminous centers of some galaxies, are powered by supermassive black holes accreting matter at astonishing rates. These objects are among the brightest phenomena in the universe, outshining entire galaxies. The connection between quasars and supermassive stars lies in their shared origins. Without the initial formation and collapse of supermassive stars, the rapid assembly of black holes required to power quasars would have been far less likely. Observing quasars at great distances, essentially looking back in time, offers a glimpse into the era when supermassive stars and their black hole descendants were shaping the universe. Interestingly, the search for observational evidence of supermassive stars continues to push the boundaries of technology and imagination. While direct observations of these stars are unlikely due to their brief lifespans and immense distances, astronomers are exploring indirect methods to detect their fingerprints. For example, certain patterns in the chemical composition of ancient stars may hint at the influence of supermassive progenitors. These second-generation stars, formed from the remnants of supermassive stars, could contain unusually high levels of specific elements, offering clues about their predecessors. Additionally, the detection of gravitational waves has opened a new avenue for studying supermassive stars and their black hole remnants. When two black holes merge, they emit ripples in spacetime that can be detected by observatories like LIGO and Virgo. Some of these mergers may involve the remnants of supermassive stars, providing a unique opportunity to probe their properties and evolution. Looking ahead, upcoming telescopes and missions promise to revolutionize our understanding of the early universe and the role of supermassive stars. The James Webb Space Telescope, JWST, with its unparalleled sensitivity to infrared light, is already offering unprecedented views of the first galaxies and stars. By examining the light from these ancient objects, scientists hope to identify the signatures of supermassive stars and better understand their contribution to cosmic history. The European Extremely Large Telescope, ELT, and other next-generation ground-based observatories will complement these efforts by providing detailed spectroscopic data, allowing researchers to analyze the chemical composition and dynamics of early galaxies in unprecedented detail. Together, these tools will bring us closer to answering the enduring mysteries of supermassive stars. How did they form? What was their impact on the universe? And what can they teach us about the nature of the cosmos itself? In contemplating these questions, it's clear that supermassive stars occupy a unique place in the cosmic narrative. They were both creators and destroyers, forging the first heavy elements while driving the processes that led to the universe's large-scale structure. Their brief but spectacular lives left an indelible mark on the cosmos, influencing everything from the formation of galaxies to the chemical composition of the interstellar medium. Yet, despite their outsized impact, supermassive stars remain enigmatic, their stories obscured by the vast stretches of time and space that separate us from their era. Each discovery brings us closer to understanding these celestial giants, but also reminds us of the universe's boundless complexity and mystery. The journey to uncover the secrets of supermassive stars is far from over, and it promises to reshape our understanding of the cosmos in profound and unexpected ways. The legacy of supermassive stars doesn't just belong to their immediate surroundings. Their influence ripples out across space and time, touching aspects of the universe we are only beginning to comprehend. Imagine them as the architects of cosmic evolution, their existence brief but so profoundly impactful that they continue to shape the universe billions of years after their deaths. The story of these stars is one of extremes, not only in size and luminosity but also in the scale of their consequences. To understand the universe as it exists today, we must trace its roots back to these primordial titans. One of the most puzzling questions about supermassive stars revolves around their formation. In the universe's infancy, the conditions were radically different from those we observe today. The lack of heavy elements meant that gas clouds couldn't cool as efficiently as they do now. This inefficiency in cooling might explain why early stars grew to such monstrous proportions. In modern star-forming regions, cooling mechanisms fragment massive clouds into smaller pieces, forming stars more in line with the sizes we see today. But in the early universe, with fewer elements to facilitate cooling, entire clouds could collapse into singular, gargantuan stars. Computer simulations offer glimpses into how this might have worked. Some models suggest that in high-density regions of dark matter, where gravitational forces were immense, supermassive stars could form directly from the collapse of gas. These stars were born in isolation, without the clustered star-forming regions we commonly see in galaxies today. Their sheer mass meant that they lived fast and died young, often burning through their nuclear fuel in just a few million years. These stars were more than just anomalies. They were catalysts for the next stages of cosmic evolution. As their intense radiation ionized the surrounding hydrogen gas, they created vast bubbles of ionized material. This process wasn't just about clearing space. It fundamentally changed how light and matter interacted in the universe. By reionizing hydrogen, supermassive stars allowed light to travel freely, lifting the cosmic veil that had cloaked the universe during the Dark Ages. Without this process, the universe as we know it, filled with galaxies, stars, and other luminous objects, might look vastly different. But the story of these stars doesn't end with their death. Their explosive or implosive fates left behind some of the universe's most intriguing phenomena. In cases where a supermassive star collapsed directly into a black hole, it created seeds for the supermassive black holes found at the centers of galaxies today. The exact mechanism by which these black holes grew to their enormous sizes is still debated, but the role of their stellar progenitors is undeniable. Supermassive black holes, like those powering quasars, might owe their rapid growth to these early stellar giants. By feeding on surrounding gas and dust, these black holes could quickly accumulate mass, transforming from relatively small remnants into the behemoths we observe today. Observations of quasars at extreme distances, billions of light-years away, suggest that supermassive black holes existed very early in the universe's history. The timescales for their formation align closely with the lives and deaths of supermassive stars, hinting at a direct connection. The gravitational waves detected from black hole mergers may also carry echoes of these ancient stars. When two black holes collide, the resulting ripples in space-time provide a wealth of information about their origins. Some of the black holes detected by observatories like LIGO and Virgo have masses that could correspond to the remnants of supermassive stars. These detections open a new window into studying these ancient objects, offering insights into their properties and evolution that were previously inaccessible. Another area of ongoing research is the chemical fingerprints left by supermassive stars. When these stars exploded, they scattered heavy elements into the surrounding medium, creating a distinctive chemical signature. By studying the composition of ancient stars and interstellar gas, scientists can infer the characteristics of the supermassive stars that preceded them. For example, certain patterns in the abundance of elements like carbon and nitrogen might point to specific nucleosynthetic processes that only occur in stars of extreme mass. As technology advances, astronomers are uncovering more evidence of these early stars and their impact. The James Webb Space Telescope is already revolutionizing our understanding of the early universe by detecting faint light from some of the first galaxies. These galaxies, likely influenced by the supermassive stars within them, provide crucial data about the conditions in the early cosmos. Future missions, such as the Nancy Grace Roman Space Telescope, promise to build on these discoveries, offering even more detailed views of the universe's formative years. Theoretical models are also evolving to accommodate new findings. For decades, scientists have debated whether supermassive stars could have formed in pairs or small groups rather than in isolation. If such pairings occurred, the interactions between these stars could have had profound implications for their evolution and the nature of their deaths. Binary or multiple systems might have produced gravitational waves or other observable phenomena, leaving additional clues for astronomers to decipher. Yet, despite all these advances, supermassive stars remain elusive. They occupy a time and space so distant from our own that direct observation is nearly impossible. Instead, we piece together their story through indirect evidence, chemical patterns, gravitational waves, and the light from ancient galaxies. Each discovery adds another layer to our understanding, but the full picture remains tantalizingly out of reach. What's perhaps most striking about supermassive stars is the sense of scale they bring to the cosmos. Their lives, though fleeting, remind us of the immense forces at play in the universe's early days. These stars were both creators and destroyers, forging the elements that make up planets and life while also driving processes that reshape the cosmos. They stand as a testament to the dynamic, ever-changing nature of the universe. A reminder that even the most colossal stars are but fleeting moments in the grand cosmic timeline. And so, the story of supermassive stars is not just about the past. It's about the questions they raise for the future. How many of these stars were there? What other roles might they have played in shaping the universe? And could their descendants, black holes, quasars, and other cosmic phenomena, hold even more secrets waiting to be uncovered? The search for answers continues, driven by our innate curiosity and the ever-advancing tools of modern astronomy. Each new observation, simulation, or detection brings us closer to understanding these cosmic monsters and their place in the grand narrative of the universe. The more we explore the universe, the more we realize how much the story of supermassive stars intertwines with everything around us. Their existence, while ancient, has consequences that echo through every corner of the cosmos, from the distribution of elements to the formation of galaxies. Yet, these celestial giants are among the most enigmatic characters in the universe's history. Their sheer size, brightness, and brevity pose significant challenges to researchers, leaving us with tantalizing fragments of information rather than a complete picture. One of the enduring mysteries is the sheer scale of these stars. How massive could they truly become? Theoretical models suggest some supermassive stars could have reached masses of up to 10,000 times that of the Sun, a staggering size compared to even the largest stars we observe today. The forces at play in these colossal objects are unlike anything we see in the modern universe. For example, the extreme gravity within a supermassive star would compress its core to unimaginable densities, driving nuclear fusion at breakneck speeds. This fusion process would generate an intense outflow of radiation, creating a delicate balance between gravity pulling inward and radiation pressure pushing outward. However, this balance was inherently unstable. The greater the mass of the star, the more violent its collapse would be once it exhausted its nuclear fuel. Unlike smaller stars, which might end their lives as white dwarfs or neutron stars, supermassive stars often bypass these intermediate stages entirely. When their cores could no longer support the overwhelming gravitational forces, they would collapse directly into black holes. This process, known as direct collapse, is believed to have been a common fate for the earliest supermassive stars. The direct collapse of a supermassive star didn't just leave behind a black hole, it also unleashed incredible amounts of energy. These events could have been the source of ultra-bright gamma-ray bursts, among the most energetic phenomena in the universe. Although modern gamma-ray bursts are typically associated with smaller stellar collapses, some scientists speculate that the brightest bursts observed from distant galaxies might be the dying screams of supermassive stars. If true, these events provide a rare glimpse into the universe's formative years, allowing us to study these stars indirectly through their explosive finales. Another puzzle is how supermassive stars interacted with their surroundings. Their intense radiation would have had profound effects on nearby gas and dust, ionizing vast regions and clearing space for the formation of new cosmic structures. In doing so, these stars may have acted as both destroyers and creators, setting the stage for the first galaxies to emerge. But the exact mechanisms by which they shaped their environment remain uncertain. Did their radiation trigger the collapse of nearby gas clouds, sparking the birth of new stars? Or did it inhibit star formation by dispersing the raw materials needed to create them? The answers likely depend on a delicate interplay of factors, from the star's size to the density of its surroundings. One of the most exciting areas of research focuses on the relationship between supermassive stars and dark matter. Dark matter, which makes up roughly 85% of the universe's mass, played a crucial role in the early universe by providing the gravitational scaffolding for gas clouds to collapse and form stars. But could dark matter have done more than just assist in their formation? Some theories propose that supermassive stars might have had cores composed partially of dark matter. These dark stars would have been unlike anything we see today, powered not just by nuclear fusion, but also by the annihilation of dark matter particles within their cores. If such stars existed, they would represent a fascinating hybrid of ordinary and dark matter, offering new insights into the mysterious substance that dominates the universe. The remnants of these stars might also hold clues about their nature. Black holes formed from supermassive stars would have unique properties, including mass ranges that differ from those of black holes formed by more typical stellar processes. Observatories like LIGO and Virgo, which detect gravitational waves from merging black holes, provide a unique opportunity to study these remnants. By analyzing the mass, spin, and other characteristics of detected black holes, scientists can infer details about their origins. Some of the unusually massive black holes observed by these facilities might be the long-lost descendants of supermassive stars, offering a rare glimpse into their legacy. Supermassive stars may also hold the key to understanding some of the universe's most perplexing phenomena. For example, the mysterious reionization epoch, a period when the universe's neutral hydrogen was reionized, aligns closely with the expected lifetimes of supermassive stars. While quasars and other luminous objects are often credited with reionizing the universe, supermassive stars might have played an equally significant role. Their intense ultraviolet radiation could have ionized vast regions of space, contributing to the transformation of the early universe from a dark, opaque state to one filled with light. Another enduring mystery is the role of supermassive stars in the formation of galaxies. Observations of distant galaxies often reveal supermassive black holes at their centers, suggesting a close relationship between these objects and their host galaxies. But which came first, the black hole or the galaxy? Some scientists propose that supermassive stars were the missing link, acting as precursors to both. Their gravitational influence could have attracted gas and dust, forming the seeds of early galaxies, while their eventual collapse into black holes provided the gravitational anchor for these galaxies to grow. If true, this scenario places supermassive stars at the heart of cosmic evolution, bridging the gap between the Big Bang and the galaxies we see today. Despite their importance, supermassive stars remain largely hypothetical. Direct evidence of their existence is scarce, given the immense distances and timescales involved. However, advances in observational technology are bringing us closer to uncovering their secrets. Telescopes like the James Webb Space Telescope are capable of peering further back in time than ever before, capturing light from the universe's earliest epochs. These observations might reveal indirect signatures of supermassive stars, such as peculiar patterns in the light from distant galaxies or unusual chemical abundances in ancient interstellar gas. Theoretical models are also evolving to keep pace with new discoveries. Simulations of the early universe now incorporate increasingly complex physics, from the behavior of ionized gas to the effects of magnetic fields. These models help scientists test different scenarios for the formation and evolution of supermassive stars, narrowing down the range of possibilities. But even the most sophisticated simulations have their limits, constrained by our incomplete understanding of the universe's fundamental laws. In many ways, the study of supermassive stars is a microcosm of astronomy itself, an ongoing quest to understand the unknown. These stars challenge our assumptions about the limits of physics, the nature of matter, and the origins of the universe. They force us to think beyond the familiar, to consider the extremes of size, energy, and time. And in doing so, they remind us of the boundless curiosity that drives scientific discovery. As we continue to explore the cosmos, the legacy of supermassive stars will undoubtedly grow clearer. Each new observation, simulation, or theory adds another piece to the puzzle, bringing us closer to understanding these ancient titans. Yet, for all we've learned, their story remains one of the greatest mysteries of the universe, a testament to the enduring power of the unknown. The mysteries surrounding supermassive stars compel us to push the boundaries of what we know and imagine. These celestial giants, both in their grandeur and their fleeting existence, represent the ultimate enigma of the early universe. The question remains, what could the universe have looked like under their influence? These stars were not just objects floating in the void. They were cosmic powerhouses that likely transformed their surroundings in ways we are only beginning to understand. A particularly puzzling aspect of supermassive stars is the timescale of their existence. Modern stars, depending on their mass, can live for billions or even tens of billions of years. Yet, supermassive stars burn through their nuclear fuel in mere millions of years, a blink of an eye compared to the lifespan of the universe. Their short-lived existence raises an important question. How did they manage to leave such a significant imprint in such a short amount of time? The key lies in their immense luminosity. A supermassive star's brightness could outshine entire galaxies, emitting extraordinary amounts of energy into the surrounding space. This energy would have ionized vast regions of gas, heating and illuminating areas that were previously cold and dark. Imagine a universe bathed in the glow of these titanic objects, their light carving out pockets of warmth and structure in an otherwise desolate cosmos. But this light wasn't without its consequences. The intense radiation pressure from supermassive stars could blow away the gas and dust in their vicinity, potentially halting further star formation. This creates a paradox. While these stars were capable of igniting new waves of cosmic creation, they could also prevent it. The balance between these opposing effects, stimulating and inhibiting star formation, likely varied depending on the local conditions around each supermassive star. Furthermore, the brevity of their lives means they didn't exist in isolation. Supermassive stars would have lived in clusters, forming in regions where gas and dark matter densities were exceptionally high. These clusters, known as protogalactic clouds, were the precursors to the galaxies we see today. Within these dense environments, the interactions between multiple supermassive stars would have been intense. Collisions, gravitational interactions, and even mutual destruction could have been commonplace, creating a chaotic and dynamic early universe. One particularly fascinating hypothesis is that these interactions may have seeded the formation of supermassive black holes. When two supermassive stars collided, the resulting mass could have exceeded the stability threshold, leading to an immediate collapse into a black hole. Over time, these black holes could have merged with others, growing larger and eventually anchoring the centers of early galaxies. This process would explain the rapid growth of supermassive black holes, which appears to have occurred much faster than traditional models of black hole accretion would suggest. Supermassive stars also challenge our understanding of the elemental composition of the universe. In their brief lifetimes, these stars would have undergone a unique form of nucleosynthesis, creating heavier elements in their cores before dispersing them during their explosive deaths. The chemical signatures of these processes are embedded in the gas and dust clouds that formed later generations of stars. By studying these chemical fingerprints, astronomers can trace the influence of supermassive stars on the evolution of the universe's elemental composition. One example of this is the abundance of elements like carbon, nitrogen, and oxygen in the interstellar medium. These elements are essential for life as we know it, and their presence in the early universe can be partially attributed to the contributions of supermassive stars. However, the exact processes by which these stars enrich their surroundings remain a topic of active research. Did they explode as supernovae, scattering their material across vast distances? Or did they collapse directly into black holes, trapping most of their elements within the event horizon? The answer may vary depending on the mass and environment of each star. Adding to the intrigue is the possibility that supermassive stars could have existed in forms beyond what we currently imagine. For example, some researchers have proposed the existence of quasi-stars, objects even larger and more luminous than traditional supermassive stars. These hypothetical entities would have formed under extreme conditions in the early universe, with cores so hot and dense that they were partially supported by radiation pressure from accreting matter. Quasi-stars would have been transitional objects, bridging the gap between stars and black holes, and their study could shed light on the formation mechanisms of supermassive black holes. Quasi-stars, if they existed, would have emitted energy at levels that dwarf even the brightest objects in the modern universe. Their luminosity could have been a critical factor in reionizing the universe, an epoch that transformed the cosmos from a neutral, opaque state to a transparent, light-filled one. Observing evidence of such objects would provide a unique window into the earliest stages of cosmic history, revealing how the first sources of light shaped the universe. The search for direct evidence of supermassive stars and their remnants is one of the most exciting frontiers in astronomy. While we cannot observe these stars directly, we can look for their footprints in the form of unusual light patterns, gravitational wave signals, and chemical abundances in ancient stars. For instance, population 3 stars, the hypothetical first generation of stars, are thought to have formed from the primordial hydrogen and helium left over from the Big Bang. If we can identify stars with elemental compositions that suggest enrichment by supermassive stars, we might gain new insights into their existence. Gravitational waves, ripples in space-time caused by massive cosmic events, offer another avenue for exploration. The merger of black holes formed from supermassive stars would produce gravitational waves with unique characteristics, potentially detectable by advanced observatories. These signals could reveal details about the masses, spins, and merger histories of these ancient objects, providing indirect evidence of their origins. The role of supermassive stars in shaping the universe extends beyond their immediate surroundings. Their influence can be seen in the large-scale structure of the cosmos, from the distribution of galaxies to the cosmic web of dark matter and gas that connects them. By studying the relationship between these structures and the early universe's energetic processes, scientists can reconstruct the chain of events that led to the universe we see today. Yet, despite all we've learned, the story of supermassive stars remains incomplete. Their existence challenges our understanding of physics, from the behavior of matter at extreme densities to the interactions between gravity, radiation, and dark matter. Each discovery raises new questions, forcing us to reevaluate our assumptions and expand our horizons. As we look to the future, the study of supermassive stars promises to be a cornerstone of astrophysical research. New telescopes, simulations, and observational techniques will undoubtedly bring us closer to unraveling their mysteries. But for now, these titanic stars remain a testament to the universe's boundless complexity, a reminder that, no matter how much we discover, there will always be more to learn. The fascinating world of supermassive stars continues to captivate the imagination of astronomers and physicists alike. These primordial behemoths, which existed in the early universe, may have been crucial to the development of galaxies, black holes, and even the conditions necessary for life to emerge. As we continue to probe deeper into the fabric of space and time, we are finding that these stars were not just transient phenomena. They were cosmic engines that helped forge the universe in ways that are still not fully understood. One of the most profound implications of studying supermassive stars is the challenge they present to our current theories of stellar evolution. In modern astronomy, we understand that stars form through the gravitational collapse of gas and dust in molecular clouds. These clouds condense, heat up, and eventually ignite nuclear fusion at their cores, creating a stable balance between the outward pressure of fusion and the inward pull of gravity. This process results in stars of various sizes, from small red dwarfs to larger blue giants. However, the formation of supermassive stars in the early universe appears to defy the standard model. In a typical star formation process, gas clouds tend to fragment and break apart into smaller clumps, each eventually forming a single star. But when it comes to supermassive stars, this process seems to have been different. Rather than fragmenting into smaller stars, the gas in the early universe could have collapsed into much larger, singular objects, which eventually grew to hundreds or even thousands of times the mass of our Sun. The exact mechanism behind this growth is still unclear. Some theories suggest that radiation pressure was not strong enough to halt the collapse, allowing the stars to keep growing as gas fell into them. This idea contrasts sharply with the formation of modern stars, where radiation pressure from fusion acts as a powerful counterforce against gravity, stabilizing the star. Interestingly, the presence of dark matter may have also played a significant role in the formation of these massive stars. Dark matter, an invisible substance that makes up a significant portion of the universe's mass, does not interact with light or other electromagnetic radiation. However, it exerts a gravitational pull on ordinary matter. In the dense regions of the early universe, dark matter may have acted as a kind of scaffolding, providing additional gravitational pull that helped gas clouds collapse into supermassive stars. This means that dark matter may have been essential in the creation of the first giants of the cosmos, further complicating our understanding of how galaxies and stars were born. Supermassive stars were also thought to have played an essential role in the creation of heavy elements. During their short, but intense, lifetimes, these stars would have undergone extreme nuclear fusion, producing a variety of elements heavier than hydrogen and helium, such as carbon, oxygen, and nitrogen. These elements would later enrich the interstellar medium, serving as building blocks for subsequent generations of stars and planets. Their death throes, whether through supernova explosions or direct collapse into black holes, would have dispersed these elements into space, contributing to the chemical diversity we see in the universe today. Moreover, the supernova explosions of these massive stars, when they occurred, would have been some of the most energetic events in the cosmos. Unlike the supernovae we observe in today's universe, which are caused by the death of stars similar in size to the Sun, the explosions of supermassive stars would have been on an entirely different scale. These hypernovae would have released colossal amounts of energy, creating shockwaves that traveled through the surrounding gas and dust, triggering the formation of new stars and galaxies. In a sense, the death of one of these stars could have been the birth of an entire new region of the universe, setting off a chain reaction that shaped the cosmos for billions of years. Yet, despite all their power and influence, these supermassive stars would have lived relatively short lives. Within only a few million years, they would have consumed all their fuel, either collapsing into black holes or exploding as hypernovae. Their rapid demise would have had profound consequences for the surrounding regions. The intense radiation they emitted would have ionized large regions of space, stripping away electrons from atoms and making the surrounding gas glow with a soft, diffuse light. This process, known as reionization, is thought to have been one of the key events in the evolution of the early universe, transforming it from a dark and opaque state into a transparent, light-filled one. The aftereffects of supermassive stars may also have contributed to the creation of supermassive black holes. It's widely believed that the first supermassive black holes formed from the collapse of these massive stars, though the precise mechanism is still debated. As these stars burned through their fuel, they would have created immense amounts of pressure at their cores, causing them to collapse into black holes. Over time, these black holes could have grown larger through the accretion of matter and the merger of other black holes, eventually becoming the supermassive black holes found at the centers of most galaxies today. There's also the possibility that the remnants of supermassive stars contributed to the formation of the first galaxies. Galaxies, after all, are not just collections of stars. They are vast, gravitationally bound systems that contain stars, gas, dust, and dark matter. The presence of supermassive stars could have acted as the seeds for these galaxies, influencing their shape, structure, and growth. The energy released by supermassive stars would have also played a role in regulating star formation within galaxies. The radiation and winds from these stars would have either triggered or inhibited the formation of new stars, depending on the conditions in their vicinity. However, the study of supermassive stars is still in its infancy. Many of the theories surrounding these objects are based on indirect evidence, such as the observation of primordial gas clouds or the chemical compositions of distant galaxies. Despite this, the excitement in the scientific community continues to build as new tools and technologies are developed that can peer deeper into the early universe. One such tool is the James Webb Space Telescope, which is expected to provide unprecedented insights into the formation of the earliest stars and galaxies. With its ability to observe infrared light, Webb can look further back in time than ever before, potentially uncovering the birth of supermassive stars. Additionally, next-generation observatories, such as the Extremely Large Telescope (ELT) in Chile and the Square Kilometre Array (SKA) radio telescope, may also provide valuable data that could shed light on the formation and evolution of these enigmatic stars. Supermassive stars also offer an opportunity to test the limits of our understanding of physics. These stars exist under conditions so extreme that they challenge our current models of stellar dynamics. Their gravity, radiation, and behavior would have pushed the boundaries of known physics, providing a testing ground for theories such as general relativity and quantum mechanics. By studying these stars, we may gain new insights into the fundamental forces of nature and the laws that govern the universe. Ultimately, supermassive stars remain one of the most tantalizing mysteries in astrophysics. Their fleeting existence, immense power, and transformative role in the universe make them essential to understanding the history of the cosmos. As we continue to probe deeper into the early universe, we may uncover more secrets about these cosmic giants, secrets that will help us unlock the mysteries of the universe's birth, evolution, and future. As our knowledge of supermassive stars continues to expand, we find ourselves uncovering more layers of cosmic history that were once obscured. These colossal stars are not only pivotal in shaping the early universe but also offer a window into the violent and energetic processes that governed its infancy. Their discovery and study are more than just a matter of scientific curiosity. They are fundamental to understanding the very nature of how our universe came to be and how it evolved into what we observe today. One of the most captivating aspects of supermassive stars is their potential to answer questions about the origins of heavy elements. While lighter elements such as hydrogen and helium were forged in the Big Bang, elements like carbon, oxygen, and iron were created later in the cores of stars. In today's universe, the process of stellar nucleosynthesis and the explosive death of massive stars through supernovae are responsible for distributing these heavier elements across the cosmos. However, in the early universe, supermassive stars may have played an even more direct role in this process. The incredibly high temperatures and pressures inside supermassive stars would have facilitated the synthesis of heavier elements much more efficiently than in today's stars. They likely produced vast amounts of elements like oxygen, nitrogen, and even metals such as iron, all of which are vital for the formation of planets and life. The supernovae or hypernovae that marked the death of these stars would have been the explosive events that scattered these elements into space, enriching the surrounding regions and setting the stage for the formation of subsequent generations of stars and planetary systems. Interestingly, recent studies suggest that the first stars in the universe, sometimes referred to as population 3 stars, may have been composed almost entirely of hydrogen and helium, the elements created during the Big Bang. These stars would have been massive, perhaps hundreds of times the mass of our Sun, and would have burned through their fuel at an astonishing rate. However, as they formed and evolved, they would have also created heavier elements in their cores through nuclear fusion, changing the composition of the universe and paving the way for the next generation of stars. The death of these first-generation supermassive stars would have been a cataclysmic event, releasing massive amounts of energy and heavy elements into space. The resulting shockwaves and radiation would have been sufficient to ionize the surrounding gas, heating it up and causing it to glow. This period, known as reionization, is a key milestone in the history of the universe. It marks the point at which the universe transitioned from being opaque to transparent, allowing light to travel freely through space. The death of supermassive stars could have been the driving force behind this transition, lighting up the universe and creating the conditions necessary for the formation of galaxies, black holes, and more stars. The role of these stars in shaping the structure of the universe is also profound. Supermassive stars were not isolated objects. They were embedded within vast clouds of gas and dust that eventually formed the first galaxies. These galaxies, in turn, acted as the building blocks of the larger cosmic structures that would follow. The radiation and winds produced by supermassive stars could have had a dramatic impact on the surrounding gas, either triggering or halting the formation of new stars within their galaxies. In some cases, these stars may have even contributed to the growth of supermassive black holes at the centers of galaxies, further influencing the evolution of the universe. Supermassive stars are also tied to one of the most enigmatic phenomena in the universe, black holes. In particular, the birth of supermassive black holes is thought to be linked to the collapse of these massive stars. While smaller stars end their lives as white dwarfs or neutron stars, the sheer mass of supermassive stars meant that they would have collapsed directly into black holes upon exhaustion of their fuel. These black holes, initially formed from the remnants of the supermassive stars, would have continued to grow by accreting matter from their surroundings, eventually becoming the supermassive black holes found at the centers of most galaxies today. There is an ongoing debate about whether these first supermassive black holes formed directly from the collapse of supermassive stars or if they were the result of a more gradual process. Some theories suggest that these black holes could have formed from the direct collapse of gas in the early universe, bypassing the need for a star to precede them. Others posit that supermassive stars were crucial in providing the initial seeds for the formation of these black holes. Either way, the connection between supermassive stars and black holes remains one of the most compelling aspects of their legacy. In the quest to understand the formation and evolution of supermassive stars, astronomers are turning to increasingly sophisticated tools and techniques. The advent of powerful observatories and telescopes, such as the James Webb Space Telescope, JWST, is allowing scientists to peer further into the universe's past than ever before. The JWST, with its ability to observe infrared light, is particularly well suited for studying the first generations of stars, including those that formed in the earliest epochs of the universe. By studying distant galaxies and their star populations, astronomers can gather valuable information about the conditions that led to the formation of supermassive stars. They are also using advanced simulations to model the behavior of gas and dust in the early universe, trying to understand how these massive objects were able to form in the first place. These simulations are crucial for testing theories about the role of dark matter and radiation pressure in star formation, helping scientists to refine their models and gain a deeper understanding of the processes that shaped the early universe. However, the study of supermassive stars is far from easy. These stars existed billions of years ago, and much of the evidence for their existence is indirect. Observing the remnants of supermassive stars is challenging, as they have long since died, leaving behind black holes or supernova remnants that are difficult to study directly. Much of the evidence for their existence comes from the observation of ancient galaxies, their chemical compositions, and the distribution of heavy elements in the universe. Yet, despite these challenges, the search for supermassive stars continues to inspire awe and wonder. As scientists continue to unravel the mysteries of these primordial giants, one thing is clear: supermassive stars were not mere curiosities of the early universe. They were central players in the formation of galaxies, black holes, and the chemical enrichment of the cosmos. Their brief but extraordinary lives set the stage for the universe we observe today, and their study will continue to push the boundaries of our understanding of the cosmos for generations to come. These enigmatic giants may have existed for only a short time, but their impact on the universe is immeasurable. As we peer deeper into the distant past and study the traces of their existence, we are not only uncovering the secrets of the early universe but also gaining insights into the very forces that govern the cosmos. Supermassive stars remind us that the universe is full of mysteries waiting to be discovered, and each new discovery brings us one step closer to understanding the incredible journey of the cosmos from its birth to the present day. As we delve deeper into the history of supermassive stars, we are confronted with a series of intriguing questions about the nature of their existence. The sheer mass of these stars challenges many of our conventional understandings of stellar formation and evolution. How did they form? What were the conditions in the early universe that allowed these cosmic giants to come into existence? And perhaps most puzzling of all, what role did they play in the creation of the first black holes? One of the key factors in understanding how these supermassive stars came to be lies in the environment of the early universe. Immediately following the Big Bang, the universe was a much different place than it is today. The first few 100 million years were marked by a period known as the Cosmic Dark Ages, during which the universe was filled with gas and dust but lacked the light from stars to illuminate the vast voids of space. This dark period was eventually followed by the birth of the first stars, which began to shine and end the Cosmic Dark Age, a process known as reionization. It is within this epoch that supermassive stars are thought to have formed. The early universe was a much denser place than it is today, with much higher concentrations of gas and dust. This allowed for the rapid accumulation of material, which in turn created the conditions for the formation of extremely massive stars. These stars, unlike those that formed in more recent times, did not have the same constraints that we observe today. Modern stars are generally limited in size due to radiation pressure, which pushes outward against the force of gravity. However, in the early universe, the gas clouds were denser, and the radiation pressure was not as significant, allowing stars to grow to colossal sizes. These supermassive stars, often referred to as population 3 stars, were likely composed almost entirely of hydrogen and helium, the two elements created during the Big Bang. They were the first generation of stars to form, and their massive size made them radically different from anything we observe in the present universe. Unlike the stars of today, which typically have a mass up to around 10 times that of the Sun, supermassive stars were thought to have masses that could range from 100 to 300 times the mass of our Sun, or even larger. The formation of these stars was likely a complex process that involved a combination of factors, including the gravitational collapse of massive gas clouds and the influence of dark matter. Dark matter, a mysterious substance that makes up a significant portion of the universe's mass, is thought to have played a crucial role in the formation of the earliest stars. Its gravitational pull may have helped draw in large amounts of gas, facilitating the rapid growth of these stars. Additionally, the relatively low levels of radiation in the early universe allowed the gas clouds to remain in a state where they could collapse more easily, providing the necessary conditions for the formation of these massive stars. The death of these supermassive stars was just as dramatic as their birth. Due to their immense size, these stars burned through their fuel at an accelerated rate, exhausting their core hydrogen much faster than modern stars. Once they ran out of fuel, they were no longer able to sustain the immense pressure needed to counteract the force of gravity. As a result, these stars underwent a violent collapse, leading to their ultimate demise in one of the most powerful explosions in the universe, a supernova or hypernova. A hypernova is an even more extreme version of a supernova, and it is thought that the death of supermassive stars likely resulted in these intense events. Hypernovae are capable of releasing an extraordinary amount of energy, far surpassing the energy released by typical supernovae. The sheer power of these explosions could have triggered the formation of black holes, which were likely the remnants of these stars. These black holes, in turn, would have continued to grow by accreting gas and dust from their surroundings, eventually becoming the supermassive black holes that we observe at the centers of many galaxies today. The connection between supermassive stars and black holes has long been a topic of scientific debate. Some researchers believe that these black holes formed directly from the collapse of the stars, while others argue that the process was more gradual, with smaller black holes merging over time to form the supermassive black holes that exist today. Regardless of the precise mechanism, it is clear that the death of these early supermassive stars was integral to the formation of the first black holes, which played a crucial role in shaping the structure of the universe. The influence of these supermassive stars extended far beyond their immediate surroundings. As their radiation flooded the early universe, it had a profound effect on the surrounding gas, helping to trigger the formation of new stars and galaxies. The energy released during the death of these stars also played a significant role in reionizing the universe, a process that ended the cosmic dark age and allowed the light from stars to travel freely through space. This period of reionization was a critical moment in the history of the universe, as it set the stage for the formation of the large-scale cosmic structures that we observe today. It is also worth noting that these supermassive stars may have been instrumental in the creation of heavy elements, a process known as nucleosynthesis. While the lighter elements like hydrogen and helium were formed during the Big Bang, heavier elements such as carbon, oxygen, and iron are thought to have been created in the cores of stars. Supermassive stars, with their extreme temperatures and pressures, would have been capable of synthesizing a wide range of heavy elements. The death of these stars, through supernovae or hypernovae, would have spread these elements throughout the universe, enriching the surrounding gas and laying the groundwork for the formation of the next generation of stars and planets. The discovery of supermassive stars and their role in the early universe has far-reaching implications for our understanding of cosmic evolution. These stars were not just massive objects that burned brightly for a short time. They were the building blocks of galaxies, black holes, and even life itself. The process of stellar evolution that began with these first-generation supermassive stars ultimately led to the diverse and complex universe that we inhabit today. As we look to the future, the study of these primordial giants will continue to be a critical area of research in astronomy and astrophysics. With the advent of new technologies and more powerful telescopes, scientists are uncovering more clues about the formation and death of supermassive stars. The James Webb Space Telescope, for example, promises to provide unprecedented views of the early universe, allowing astronomers to study the remnants of these first-generation stars and the galaxies they formed. Additionally, advanced computer simulations are helping to refine our models of star formation, providing a clearer picture of how these massive objects came into being. As our understanding of supermassive stars deepens, so too does our appreciation for the intricate and often violent processes that have shaped the universe. These stars were not just the largest and most luminous objects in the early universe. They were the architects of the cosmos, influencing everything from the formation of galaxies to the creation of heavy elements. Their legacy lives on today in the black holes at the centers of galaxies, in the elements that make up our planet, and in the light from distant stars that continues to illuminate the vast expanse of space. The mystery of supermassive stars is far from solved, and there is much more to learn about these cosmic giants. What we do know is that they were far more than just fleeting objects in the universe's history. They were the catalysts of cosmic evolution, and their influence will continue to shape the universe for billions of years to come. The mysteries surrounding supermassive stars stretch beyond their explosive deaths and their roles in the formation of black holes. These early stars, with their extreme properties, offer us insights into the conditions of the primordial universe, revealing not only the birth of cosmic structures but also the seeds of life itself. Their formation and ultimate demise were pivotal in the early stages of the universe's evolution, and the impact of their existence ripples through time, influencing the very composition of galaxies and stars that followed. One of the fascinating aspects of supermassive stars lies in their potential connection to the formation of the first galaxies. These enormous stars likely acted as the gravitational anchors for the earliest clusters of gas and dust, helping to pull matter together and create the first organized structures in the universe. Their intense radiation and stellar winds could have influenced the gas around them, driving it to cool and condense, which would have allowed the formation of more stars and even entire galaxies. In a sense, these supermassive stars may have been the scaffolding upon which the early universe's cosmic architecture was built. In the grand timeline of cosmic evolution, the birth of galaxies is one of the most important milestones. And yet, the formation of these galaxies didn't happen in a vacuum. Supermassive stars played a critical role in shaping the environment in which galaxies could begin to take form. As they formed, they emitted vast amounts of radiation, contributing to the reionization of the universe. This process not only ended the cosmic dark ages but also played a key role in making the universe transparent to light, which allowed the first stars and galaxies to shine freely. But the influence of these supermassive stars wasn't restricted to their immediate surroundings. Their explosive deaths, whether as supernovae or hypernovae, spread heavy elements into space, enriching the interstellar medium and making it possible for subsequent generations of stars to form. These explosions generated the very building blocks for planets and life, ensuring that the universe could evolve into a more complex state. The material ejected by these stars, from carbon to iron, would eventually be incorporated into new stars and planetary systems, giving rise to the diversity of matter that we observe today. What's equally fascinating is that the remnants of these supermassive stars are believed to be the ancestors of the supermassive black holes found at the centers of galaxies today. The connection between the formation of these stars and the emergence of supermassive black holes presents an unresolved question in modern astrophysics. Did the black holes form directly from the collapse of the supermassive stars, or did they emerge from the gradual accumulation of mass over time, drawing in gas and dust from their surroundings? This question remains one of the most intriguing mysteries in our study of the early universe. Furthermore, these supermassive black holes would have continued to grow by accreting material, eventually becoming the supermassive black holes we observe at the hearts of galaxies today. It's worth noting that these black holes are not just passive remnants of ancient stars. They actively shape the dynamics of galaxies and even influence the formation of new stars. The powerful jets of energy emitted by supermassive black holes can strip gas and dust from surrounding regions, suppressing the formation of new stars and regulating the growth of the galaxy. In this sense, the black holes created by supermassive stars might have played a role in controlling the evolution of galaxies, limiting their size and growth over time. However, the understanding of supermassive stars and their legacy doesn't end with black holes. The study of these stars also sheds light on the origins of the first elements, which were forged in the hearts of stars like these. During their short lifetimes, supermassive stars underwent nuclear fusion at a rate far higher than any star in the modern universe, creating an unprecedented number of heavy elements. As they exploded in supernovae or hypernovae, they released these elements into the surrounding cosmos, enriching the material that would eventually form new stars, planets, and even life itself. The birth of heavy elements, such as carbon, nitrogen, and oxygen, is essential for the development of planets and life as we know it. In fact, the creation of these elements through stellar nucleosynthesis is a crucial step in the process of cosmic evolution. Without the violent deaths of these supermassive stars, the complex elements necessary for life could never have been created. The study of their role in element formation is a reminder of the interconnectedness of the cosmos, where even the death of a star leads to the creation of new life and new structures. As scientists continue to probe the early universe, new technologies promise to unravel even more about these ancient stars. The advent of the James Webb Space Telescope, with its advanced infrared capabilities, allows us to peer deeper into space than ever before, providing us with a clearer view of the early universe. The telescope's ability to capture the faint light from the first stars and galaxies will be key in answering lingering questions about supermassive stars. Observing the remnants of these early giants could provide clues about their composition, their influence on the surrounding environment, and their role in the formation of black holes. In addition to observational advancements, theoretical models and computer simulations have also played a crucial role in advancing our understanding of supermassive stars. These simulations, which model the physics of star formation and evolution, help us better understand how these massive objects could have formed under the extreme conditions of the early universe. With each new iteration of these models, our understanding of the mechanisms that govern star formation and the role of dark matter, gas, and radiation in the creation of these objects becomes clearer. Despite the progress that has been made, there are still many questions that remain unanswered. How exactly did these stars form, given the extreme conditions of the early universe? Did they form through the collapse of massive gas clouds, or did they emerge from the accumulation of dark matter? What factors controlled their size and luminosity? And perhaps most intriguingly, how did the processes that led to the formation of supermassive stars contribute to the cosmic events that followed, such as the creation of galaxies and the formation of supermassive black holes? The study of supermassive stars is not just about understanding the past. It also has profound implications for our understanding of the future. The evolution of galaxies, stars, and black holes is a dynamic and ongoing process, and by studying the origins of these cosmic objects, we can gain insights into how the universe will continue to evolve. The remnants of supermassive stars, in the form of black holes and heavy elements, will continue to shape the cosmos for billions of years to come, influencing the formation of new stars, planets, and even life itself. The mystery of supermassive stars is a tale of cosmic birth and death, of forces far beyond our everyday understanding, and of processes that shape the very fabric of the universe. These stars were not just the largest and most powerful objects in the early universe. They were the catalysts of cosmic evolution, influencing the creation of galaxies, the formation of black holes, and the synthesis of the elements necessary for life. Their legacy lives on in the black holes at the centers of galaxies, in the elements that make up our planet, and in the ever-expanding universe that continues to evolve. Through ongoing research and exploration, scientists will continue to uncover the secrets of these ancient giants, shedding light on the origins of the universe and the forces that govern its evolution. The study of supermassive stars reminds us of the vastness and complexity of the cosmos, and it challenges us to ask deeper questions about our place in the universe and the mysteries that lie ahead. The more we uncover about supermassive stars, the clearer it becomes that their study is crucial to understanding not only the early universe but also the ongoing evolution of the cosmos. These celestial giants were not merely an anomaly in the cosmic timeline. They were a defining feature of the early stages of the universe's development, shaping the structures and dynamics we observe today. One of the ongoing puzzles regarding supermassive stars is how they were able to form in the first place. Current astrophysical models suggest that these stars likely emerged in the first few 100 million years after the Big Bang, during a period known as the Cosmic Dawn. The conditions of the early universe were vastly different from what we see today. There was no stardust from previous generations of stars, and the matter that existed was predominantly hydrogen and helium, the simplest and lightest elements. The high density and temperature of the gas clouds in the early universe made it possible for supermassive stars to form, despite the fact that such stars would be unstable by modern standards. But how exactly these conditions came together remains one of the most compelling mysteries in cosmology. One hypothesis suggests that the early universe contained vast clouds of pristine hydrogen gas, known as population 3 clouds. These clouds were almost completely devoid of heavy elements, which would later form as a result of stellar evolution and supernova explosions. Because these clouds lacked the cooling mechanisms that would be provided by the presence of heavier elements, they were able to collapse under their own gravity more efficiently than gas clouds in later generations. The result was the formation of stars that were far larger and more massive than anything we observe today. These massive stars, in turn, would have had much shorter lifespans, burning through their fuel at an extraordinary rate and exploding in massive supernovae, or even hypernovae. Another theory focuses on the role of dark matter in the formation of these supermassive stars. Dark matter, which makes up a significant portion of the universe's mass, interacts with regular matter through gravity, but not through electromagnetism, meaning it doesn't directly influence things like light or radiation. The idea is that dark matter might have played a role in providing the necessary gravitational collapse that allowed gas clouds to form supermassive stars. This is still speculative, but it's a fascinating possibility that researchers are continuing to explore. Whatever the exact mechanism of their formation, it's clear that the early supermassive stars had an outsized influence on the cosmos. Their sheer size meant they were capable of exerting extreme pressure and heat at their cores, resulting in intense nuclear reactions that produced vast quantities of radiation. This radiation was not just an incidental byproduct, it played a critical role in shaping the surrounding environment. The intense heat and light from these stars would have ionized the surrounding gas, creating vast bubbles of ionized hydrogen in a process known as reionization. This would have had far-reaching consequences, not only for the evolution of the early universe but also for the formation of galaxies. The presence of these stars in the early universe also sets the stage for the emergence of the first galaxies. These early supermassive stars acted as the gravitational nuclei around which the first galaxies began to form. The gravitational pull of these stars, combined with the dense environment of the early universe, created a framework in which gas and dust could collapse and form stars. Over time, these stars aggregated into galaxies, which grew ever larger as more and more stars were formed. It's worth noting that the process of galaxy formation in the early universe was far more chaotic than what we see today. Galaxies were smaller and less stable, and their formation was deeply influenced by the interactions between supermassive stars and the surrounding gas and dark matter. While the ultimate fate of these supermassive stars was often tragic, most would end their lives in violent explosions, their legacy continues to shape the universe in profound ways. The materials that these stars expelled during their deaths enriched the surrounding gas, providing the building blocks for future generations of stars, planets, and even life. The heavy elements that were created in the cores of these massive stars, such as carbon, oxygen, and iron, would eventually be incorporated into new stars and planetary systems. This process, known as stellar nucleosynthesis, is fundamental to the formation of everything we see around us. Without the contributions of these early supermassive stars, the universe would be a very different place. In a more dramatic turn, the collapse of a supermassive star could result in the formation of a black hole. Theoretical models suggest that these early black holes may have been the precursors to the supermassive black holes that we observe at the centers of galaxies today. If these black holes formed from the collapse of a star, they would have started out small but rapidly grown by accreting gas from their surroundings. Over time, they would have merged with other black holes or absorbed massive amounts of gas, eventually becoming the supermassive black holes that now reside at the heart of nearly every large galaxy. This suggests that the evolution of supermassive stars is intimately tied to the formation of the largest and most mysterious objects in the universe. Moreover, supermassive stars may have contributed to the phenomenon of cosmic inflation, the rapid expansion of the universe in its earliest moments. During the formation of these stars, they would have emitted vast amounts of energy, some of which could have influenced the early expansion of the universe. The energy released by their deaths and the subsequent formation of black holes may have been a critical factor in shaping the large-scale structure of the universe. This is a theory that is still being debated, but it underscores the idea that these early stars were not merely an isolated phenomenon. They were key players in the larger drama of cosmic evolution. The study of these stars, while still in its infancy, is revealing an extraordinary story of the universe's infancy. Supermassive stars, with their incredible size and power, were among the first objects to challenge the laws of physics as we understand them. Their formation, life cycle, and death are a testament to the extreme conditions that prevailed in the early universe. They stand as monuments to the forces that shaped everything that came after them, the galaxies, the stars, the planets, and the life that eventually emerged. The mystery of supermassive stars is more than just an academic curiosity. It is a story that connects the birth of the universe to the present day, a reminder that the forces that shaped the cosmos were not always predictable, or even comprehensible. These stars are relics of a time when the universe was young and chaotic, and their study may yet yield answers to some of the most profound questions in science. How did the first stars form? What role did they play in shaping the universe? And what does their existence tell us about the future of the cosmos? As scientists continue to unlock the secrets of these ancient stars, we find that they offer us more than just a glimpse into the past. They provide us with clues about the future, about how the universe will continue to evolve and what new mysteries lie ahead. The legacy of these supermassive stars may still be unfolding, and as we look deeper into the cosmos, we may discover that the story of the universe is far from over. As we continue to explore the remnants of these supermassive stars, the insights they provide continue to expand our understanding of cosmic history. These stars may have lived brief, intense lives, but their influence reached far beyond their immediate environments, shaping the course of the universe for billions of years. From their explosive deaths to their potential link to the formation of supermassive black holes, supermassive stars were, in many ways, the catalysts for many of the structures we see today in the universe. One of the most fascinating aspects of supermassive stars is their role in triggering cosmic events that rippled through the fabric of spacetime. When these stars exploded, their supernovae or hypernovae unleashed unimaginable amounts of energy into the cosmos. The sheer intensity of these explosions was so great that they likely created shockwaves capable of influencing the surrounding matter, heating up gas clouds and pushing them away, potentially even preventing further star formation in the immediate area. But in other cases, these explosions might have also acted as a gravitational catalyst, compressing nearby gas and dust, leading to the formation of new stars and galaxies. The energy and elements they released during their violent deaths played a critical role in the subsequent birth of new cosmic structures, ensuring that the universe was in a constant state of flux and rebirth. The supernovae that resulted from the deaths of these supermassive stars also had a profound impact on the chemical composition of the universe. These stars were capable of fusing heavier elements in their cores, elements like carbon, oxygen, and iron, that would not have been produced in the Big Bang. When the stars died, they expelled these elements into the surrounding gas, enriching the universe with the building blocks for future stars and planets. This process, known as chemical enrichment, is fundamental to the formation of life as we know it. Without the materials produced in the hearts of these massive stars, the universe would have been a much more barren place. In many ways, supermassive stars acted as the universe's first chemical factories, creating the elements that would later form everything from planets to life itself. They laid the groundwork for the chemical complexity that would eventually give rise to the stars, galaxies, and planetary systems that we see today. Without their contributions, the universe might have remained a sterile, lifeless place, without the diversity of elements required for the development of complex structures. Beyond their role in chemical enrichment, the deaths of supermassive stars also set the stage for the creation of some of the most enigmatic and powerful objects in the universe, black holes. As we know, when the most massive stars die, they can collapse under their own gravity, forming black holes, regions of space where gravity is so intense that not even light can escape. In the case of supermassive stars, their collapse would have been incredibly dramatic, resulting in the formation of black holes that were many times larger than the ones we observe today at the centers of most galaxies. The formation of these early black holes is crucial for understanding the growth and evolution of supermassive black holes in the centers of modern galaxies. The connection between supermassive stars and the black holes they may have formed is still an area of active research, but it is clear that these early black holes were likely the seeds from which the supermassive black holes of today grew. Over time, these early black holes would have consumed vast amounts of surrounding gas and dust, growing larger and larger until they became the supermassive black holes that we now find at the centers of galaxies, including our own Milky Way. But the connection between supermassive stars and supermassive black holes goes beyond mere formation. It's possible that the intense radiation and energy emitted by these early stars had an impact on the black holes themselves. As these stars collapsed and formed black holes, the release of energy could have influenced the growth and behavior of these black holes, potentially even accelerating their development. This suggests that supermassive stars played a key role not only in the formation of black holes but also in their subsequent growth and evolution. As we look deeper into the cosmos, we find that supermassive stars are not only a relic of the past but also a clue to understanding the future. Their violent deaths and their role in the formation of black holes raise important questions about the long-term fate of the universe. Will the black holes that formed from the collapse of these stars continue to grow, eventually consuming entire galaxies? Will they play a role in the eventual heat death of the universe, as they devour all matter in their path? These are questions that remain unanswered, but they point to the profound importance of understanding the role of supermassive stars in the cosmic order. In addition to their role in the formation of black holes, supermassive stars also had a major influence on the structure of galaxies. The energy they released during their lifetimes and upon their deaths helped to shape the galaxies they inhabited. These stars acted as gravitational anchors for the gas and dust that would later form new stars, and their intense radiation likely played a role in determining the sizes and shapes of the galaxies themselves. Some researchers believe that the presence of supermassive stars at the centers of early galaxies may have contributed to the formation of spiral galaxies and the large-scale structures that we observe today. As we continue to study the remnants of these stars, scientists are uncovering new insights into the processes that govern their formation and death. Observations from telescopes like the Hubble Space Telescope and the James Webb Space Telescope are allowing researchers to peer deeper into the early universe than ever before, revealing evidence of these early stars and the black holes they may have created. These observations are helping to refine our models of the early universe and improve our understanding of how galaxies, stars, and black holes evolved. Furthermore, studying supermassive stars can also provide clues about the nature of dark matter. As we know, dark matter is one of the most elusive substances in the universe. It doesn't emit light or interact with electromagnetic radiation, making it virtually invisible to our current instruments. However, its gravitational effects are undeniable, and its presence is felt in the motion of galaxies and galaxy clusters. Some scientists believe that dark matter played a role in the formation of supermassive stars, helping to provide the necessary conditions for their creation. This theory is still speculative, but it offers an intriguing possibility for how dark matter might have influenced the early universe. In the grand scheme of things, the study of supermassive stars is about more than just understanding these individual objects. It's about unraveling the story of the universe itself, how it began, how it evolved, and where it's headed. These stars were among the first objects to form in the universe, and their story is intimately tied to the larger narrative of cosmic history. Their role in the formation of galaxies, black holes, and the chemical enrichment of the universe cannot be overstated. But the mysteries surrounding these stars are far from solved. While we have made significant strides in understanding their formation, evolution, and eventual death, many questions remain. How did they form in the first place? What exactly were their life cycles like? And how did they contribute to the formation of the cosmic structures we see today? These are questions that continue to challenge scientists, and the answers may hold the key to some of the deepest mysteries of the universe. As our tools and techniques continue to improve, we will undoubtedly gain a deeper understanding of these cosmic giants. Whether through the observation of distant galaxies, the study of black holes, or the exploration of dark matter, the legacy of supermassive stars is one that will continue to shape the future of astronomy and our understanding of the universe. These stars were the first beacons in a dark, young universe, lighting the way for the galaxies, stars, and planets that followed. Their story is far from over, and as we look to the future, we may find that the mysteries of these supermassive stars are just beginning to unfold. As we continue to explore the mysteries surrounding supermassive stars, we dive deeper into their significance in shaping not only their immediate surroundings but also the entire cosmic environment. These stars were far more than just massive, luminous objects. They were the catalysts for the universe's grand evolutionary processes. Their immense mass, the gravitational pull they exerted, and the violent ends they met influenced the formation of galaxies, black holes, and even the very fabric of space-time itself. One of the most compelling aspects of supermassive stars is their role in the early universe's star formation rate. Before they existed, the universe was made up mostly of hydrogen and helium, the two lightest elements, created in the aftermath of the Big Bang. These early conditions created a universe that was remarkably simple in terms of chemical composition. However, the formation of supermassive stars marked a dramatic shift. These massive objects, born from the primordial gas clouds, acted as the universe's first superconductors, initiating complex processes that would lead to the creation of heavier elements. Through their extraordinary gravitational influence, supermassive stars played a vital role in the formation of the first galaxies and the complex cosmic structures we observe today. In terms of their own evolution, supermassive stars had an extremely short lifespan relative to other stars. While a typical star like our Sun can burn for billions of years, supermassive stars only lasted for a few million years before they exhausted their fuel. Their core temperature reached unfathomable levels, causing them to burn through their hydrogen and helium supplies at an accelerated rate. As they neared the end of their lives, the sheer pressure and temperature in their cores triggered rapid fusion of heavier elements, including carbon, oxygen, and even iron. This intense fusion process not only fueled the star but also created an environment ripe for the formation of heavier and more complex elements that would go on to populate the universe. The supernova explosions of these stars were unlike any we see today. Due to their enormous mass, these stars underwent what is known as a pair instability supernova, an event so powerful that it could completely obliterate the star, leaving behind either a black hole or, in some cases, a neutron star. These explosions were among the brightest and most energetic events in the universe, emitting vast amounts of radiation and dispersing heavy elements into space. This cosmic alchemy was essential for the birth of future generations of stars and planets, providing the raw materials necessary for the formation of the complex structures that would eventually give rise to life as we know it. Moreover, the explosions of these supermassive stars influenced the surrounding interstellar medium in ways that scientists are still trying to understand. The shockwaves generated by the supernovae would have propagated through the surrounding gas, compressing and heating it, triggering the formation of new stars. This feedback loop of star formation and destruction, initiated by the deaths of supermassive stars, helped shape the early structure of galaxies. The initial bursts of energy from supernovae may have also contributed to the ionization of the early universe, a process that occurred during the cosmic reionization period, when the first stars and galaxies began to light up the otherwise dark cosmos. A particularly intriguing consequence of the explosions of supermassive stars is their connection to the formation of supermassive black holes. These black holes, some of which reside at the centers of nearly all large galaxies today, are thought to have been seeded by the collapse of these early massive stars. When these stars died, their cores collapsed under the force of their own gravity, and depending on the star's mass and the dynamics of the collapse, they could have formed black holes with masses far greater than those typically seen today. These primordial black holes were likely the building blocks for the supermassive black holes that now reside at the centers of galaxies, including our own Milky Way. The relationship between supermassive stars and supermassive black holes is a key area of research. Some scientists speculate that these black holes may have played a role in regulating the growth of galaxies. As supermassive black holes consume surrounding matter, they emit powerful jets of radiation that could potentially inhibit the formation of new stars, controlling the size and growth of galaxies over time. This feedback mechanism may have helped shape the universe's large-scale structure, influencing the way galaxies cluster together and evolve. As we attempt to piece together the cosmic puzzle, the legacy of supermassive stars extends beyond their immediate influence. They also left behind observable markers that scientists can study today to better understand the conditions of the early universe. For example, the observation of distant quasars, intensely bright objects believed to be powered by supermassive black holes, provides a window into the universe's infancy, offering insights into the environments surrounding these early black holes and the role that supermassive stars may have played in their formation. The study of supermassive stars also has implications for understanding the universe's future. As we observe the remnants of these stars, such as the black holes they created, we are not just looking into the past but also gaining clues about the universe's long-term evolution. Will the supermassive black holes that formed from these stars continue to grow, potentially consuming entire galaxies? And what role will they play in the ultimate fate of the universe? Some theories suggest that black holes will continue to grow and merge, eventually dominating the cosmic landscape, leading to a scenario known as the Big Freeze, where galaxies, stars, and even black holes are so spread out that the universe will appear cold and dark, devoid of the structures that we associate with the cosmos today. At the same time, other theories suggest that these black holes may eventually reach a point where they can no longer grow, perhaps evaporating due to a process called Hawking radiation. This would mark the end of a cosmic cycle, where the remnants of these supermassive stars and their associated black holes slowly fade away over vast timescales. As telescopes like the James Webb Space Telescope continue to peer deeper into the universe, we are beginning to uncover more and more about the earliest phases of the cosmos, including the elusive supermassive stars that once ruled the heavens. These observations may soon provide us with the missing pieces of the puzzle, allowing us to refine our understanding of the birth and death of stars, galaxies, and black holes. The discovery of even more distant galaxies and quasars will allow scientists to study the conditions of the early universe in unprecedented detail, offering new insights into the forces that shaped the universe as we know it. In the end, supermassive stars were not just giant objects in the sky, they were cosmic architects, shaping the very structure of the universe. Their creation, evolution, and eventual death set in motion a chain of events that would lead to the formation of galaxies, stars, and planets. These stars may be long gone, but their legacy endures in the black holes that continue to shape the cosmos, in the chemical elements scattered across space, and in the galaxies that continue to evolve. As we continue to study them, we may uncover even more mysteries, unlocking the secrets of the universe's earliest days and deepening our understanding of the cosmos itself. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.